So today we're going to kind of continue on with our practice exam problem and look at basically our second dealing with thin-walled pressure vessels and then Wheatstone bridges as usual. So let's go ahead and get started. So we are trying not to burst C.elegans. So C.elegans is our transparent worms used a lot for research. So they are 1 millimeter long, diameter of 0.1 millimeters. Thickness of the skin is 5 micrometers. So you heard diameter, you heard thickness. So we know that our radius is equal to 0.05 times 10 to the minus 3 meters. Our thickness, T, is equal to 5 times 10 to the minus 6 meters. Blah, 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 blah. There's lots of kind of words in here. And we could see Young's modulus of C.elegans is 100 megapascals. We know that it is a biological or polymeric material, so nu is equal to 0.4. The gauge resistance is 120. That's just useful for our Wheatstone bridge. So I remember 1, 2, 3, 4. We know that our total strain is going to be equal to, in the standard configuration, epsilon sub 1 minus epsilon sub 2 minus epsilon sub 3 minus epsilon sub 4. But in this problem, you can see that there's only one, so the rest of these are just resistors. Resistor, resistor, so we don't have to worry about any of these. So we are at quarter bridge configuration. Gauge factor is 2.7, so let's just kind of write this out. 106 pascals. We know that our F is equal to 2.7. 2.7. Bridge is powered by 2-volt source, so VI equals 2 volts. And after pressurization, the Wheatstone bridge measured 100 millivolts. So our delta V naught is equal to 100 times 10 to the minus 3 volts. So from this information given, we know we're going to probably use delta V naught, VI, F, 4, epsilon 1 minus epsilon 2 minus epsilon 3 plus epsilon 4. So it says determine the change in pressure quantitatively. So again, we need to confirm that R over T is greater than or equal to N. Once we do that, we could jump to our thin-walled pressure vessel. So delta P, R over T. We know that L is equal to sigma H over 2. We also know that our stress tensor is going to be, if I kind of orient it basically this way. So if my coordinate system is going along or kind of around my circumferential, 2 is my H. Here is my longitudinal, my 1 direction. So I will have in the 1 direction sigma L, sigma H, and the rest of these are all 0. Close that up. My strain tensor will be similarly L 0, 0, 0, H 0, 0, 0, 0. And there we go. Now, and we also have kind of these relationships that basically epsilon sub L is equal to 1 over E times sigma L minus nu sigma H. And same thing similarly for H, 1 over E times sigma H minus nu sigma L. So let's look at, we need now, so we know we have this, we have this, we have this. We're trying to figure out the pressure quantitatively as well as all the stresses and strain measurements. So we need to figure out what are the stresses and strain quantitatively. And it says that C.elegans will tend to fail at regions of high shear stress and will actually fracture when the stress exceeds 1 megapascals. Will the worm pop? So let's get to this first question first. So we know that all the rest of these are 0. So what is the strain in 1? Well, obviously we have, again, we're looking at what's going to happen to the wires. We're going to elongate basically, so the strain in 1, they are going to elongate to this epsilon, strain in the longitudinal direction. And you see that up here, because we only have basically this, we only have this quarter bridge, and you can see that compression. So in your hoop stress will kind of basically pull these up, and that's going to lead to some Poisson's ratio of contraction. That's already encapsulated in your E sub L here. So that's all we're going to deal with this E sub L and this epsilon sub 1 for this particular stress state. So let's go ahead and start to plug in and assign some values. So we said that our R is equal to 0.05 times 10 to the minus 3. My T is equal to 5 times 10 to the minus 6. We said that our Y was equal to 100 times 10 to the 6. We also said that our nu was equal to 0.4. We also said that our F gauge factor was 2.7. VI was equal to 2 volts, and our del V naught is 100 millivolts. That's 3. And there we go. So let's check that we are in thin walled pressure vessel before we go any further. What's our R over T value? Chug along, thinking. There we go. So we are a thin walled pressure vessel, so del P times R divided by T. Sig L is equal to sig H divided by 2. There we go there. We know our E sub L is equal to 1 divided by Y times sig H minus nu, or sorry, sig L minus nu times sig H. And our E sub 1 is equal to E sub L. So we also know our stress tensor, which we've defined there, sig L, 0, 0, 0, sig H, 0, and 0, 0, 0. So that's my stress matrix form, which is this. I'm going to also define my E sub H up here, E sub H. So we're asked for that in this problem as well. 1 divided by Y times sig H minus nu times sig L right here. So let's do our strain. That was again equal to, in my coordinate system, your coordinate system can be a little bit different depending on how you orient your system, but there should be the same number of components. 0 and 0, 0, 0 for the rest. Strain matrix form. So you see that now we only are basically left with an equation. We just need to figure out del P. So I'm going to solve for my kind of fundamental equation del V naught divided by VI, set equal to F divided by 4. F divided by 4 times E1. Solve for del P. And there's my del P right there. So I'm going to say my del P goes to right there equals this. Excuse me. Let's just make sure that E sub 1 is equal to E sub L. Yep, that's all we've got there. Make sure all our values are defined correctly. R over T, 100. Yep, we're looking good to go here. So now all we have to do is plug and chug for the rest. So what is our strain? It is going to be that. What is our stress? Right there. So that's our stress. And so determine the change in pressure quantitatively. So we figured that out. That was our delta P. We figured out our stress and strain tensors, stress, strain. So we measured all those values, looking pretty good right there. Now, it's saying C.elegans will tend to fail at regions of high shear stress and will actually fracture when the stress exceeds 1 megapascal. So this is getting at our old pal of our 3D Mohr circle, or our Mohr circle. So in our three-dimensional, or our maximum shear stress values, for our 3D Mohr circle, we're already, if you look up here, we're already in our principal stress state. So I know that my sigma H, this is my sigma L, this is 0. So here, that's my big circle here. So I know that I'm going to hit my maximum shear value. My maximum my shear in this stress state is just going to be sigma H minus L, or minus 0, excuse me, divided by 2. So let's look and see what that value is. So let me look at sigma H. Let me divide that by 2. So 37 megapascals. So that worm is unfortunately going to pop. So yeah, that's it for this problem. So go ahead and yeah, if you have any questions, please let me know. Again, the key thing here is in that longitudinal direction here, because of this quarter bridge configuration, you just have that's already encapsulated in. So this minus nu sigma h tells you that strain, basically the reduction in strain due to that Poisson's ratio. But yeah, let me know if you have any questions, and thanks. Bye.